Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will discuss a very important inequality, Markov's inequality. Actually, what we will do is providing a proof of this result. Let's begin. So let me show you the statement, of Markov's inequality. Let's see what the conditions are so we can use that inequality, so that inequality holds. So if x is a random variable that takes only non-negative values, let's think for a sec an example of such a random variable x that takes only non-negative values. For instance, an exponential, right? An exponential random variable with parameter beta. You know, the non-zero part for an exponential is, values that are non-negative. Okay, so that would work as a particular example of a random variable x that takes only non-negative values. So if we have one of those and we take a positive number a, then it turns out that the probability that x is greater or equal to a is less than or equal to the expected value of your random variable divided by the number a. Okay, now let me just say something before we provide a proof of that inequality. This inequality is really important because you can use it to derive other inequalities, and the main thing is that this guy is going to allow you to find bounds for the probability of some events of interest. Make sense? Okay. So, proof. First, let me say that we're going to give a proof for the case where x is continuous with probability density f. Okay, so we give a proof for the case where x is continuous random variable with PDF f of x, say, right? Okay, nice. First, let me go back for a sec to the expression of the inequality. So we're going to start with the expected value of x here. Okay. So by definition, in this case, right, we have a continuous random variable with a PDF. So the generic formula would be, we know, it's the integral from negative infinity to infinity of x times f of x dx, right? Okay. Now, we are told that just like, as we said, just like the exponential, right? This is a non-negative random variable. So that means that it's going to be non-zero only in the interval from 0 to infinity, right? So let me just, break this down into two, like this. Oops. So the only part that matters is from 0 to infinity, right? Just like for an exponential. Okay, so next we have, let me go back to this, we have a number a. So we want to find the probability that x is greater or equal to a. Somehow we want to make it appear. If you think about it, if you had to rewrite that probability, the probability that x is greater or equal to a, right, it would be the integral from a to infinity of your PDF, right? So somehow we would like to have that kind of expression. Again, the probability that x is greater or equal to a is the integral from a to infinity of f of x dx, right? So let's see if somehow we can transform this into something like that. So a first step in that direction would be breaking down this integral into two integrals. Something like this. We could have the integral from 0 to a, right? And a is positive, so that's good. It lives between 0 and infinity. And then the other part from a to infinity, right? These two integrals are equivalent to this one. And again, if you go back to the expression of the inequality, you go, oh, I would like to have excuse me, here the probability of x greater or equal to a would be the integral from a to infinity of f of x dx. Okay, so we are getting there. Now we know, right, that x, the random variable x, assumes only non-negative values. So these two integrals are going to be positive, right? So if I remove the first one, then the sum of these two integrals is going to be greater or equal than just having the second one. Okay, so let me write that down. These two together are greater or equal than this one. Make sense? Okay, now I want you to take a look at the region where we are integrating. So this is just x is just a variable that varies from a to infinity. So the x's that we are considering here are equal to a or greater than a. So if I set this, if I fix it to be a, right, a is going to be the smallest of the possible values for the x's, which means that the integral of let me copy paste this, it's going to be useful, which means that the following integral this guy, if the x's are allowed to vary from a to infinity, right, again, worst case scenario, x equals a, but you know, it could be greater than that. If I fix that guy to be a, well, that integral must be greater or equal to this one. Makes sense, right? Because, you know, we're just fixing the value of x to be the smallest possible, right? Okay, now can you see that we're almost there? By the linearity of integrals we get to pull out that a, right? So let me do that next. So we pull out that integral here, and guess what? The integral from a to infinity of the PDF is just the probability that x is greater or equal to a, right? So what we have here is this: a times the probability that the random variable x is greater or equal to a. Make sense? So what we have shown thus far is that the expected value of x is greater or equal to a times the probability of x greater or equal to a, right? So let me rewrite that. Let me copy paste this here. The expected value of x is greater or equal, right? That's what we showed here. Expected value greater or equal to this, right? So since a is positive, we can divide by a, and the direction of the inequality is not going to change. So just let me say that dividing by a and that is exactly what we wanted to show. Okay? Well, that's it. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.